Jonathan, you ready?
Yes.
Okay, here we go. So next up, Jonathan Rizzo, KC3EEY. Title of his talk is Ground-Based VLF Observation of Whistler Waves.
Hi, I am Jonathan Rizzo. I came with Nathaniel, and he was interested in some of the hobby work that I was doing. I am a student at the University of Scranton, BSEE. I also work full-time, so if there's any mistakes in the presentation, just bear with me. So I've been working on this for since about 2013. I've been reading about natural radio and VLF, and I've built a couple of receivers, and I just wanted to tell everybody about it. First, what I wanted to do was I wanted to give an introduction to natural radio and the type of emissions that you would see. So this is Earth's natural radio. Whistlers and other natural radio emissions are naturally occurring. So that means that they're generated by some sort of physical phenomena, such as lightning discharges or interactions with ionospheric plasma. Natural radio emissions are more just static and noise. Normally, like, when there's a thunderstorm, you would turn on your radio and you would hear the pops and crackles from lightning. But there's a lot more to it. Many of these emissions undergo interesting propagation effects and can be used to understand the ionosphere and the McGreevy. This is what kind of intrigued me, that there's a lot of physics behind this. Natural radio in the VLF band is not really well known by the general public. It's not a very, kind of like a niche topic. The most interesting emissions occur in the very low frequency band and the ultra low frequency band, which is what I'm interested in. So the ITU designates the very low frequency band between 3 kilohertz and 30 kilohertz. And ULF, which these emissions fall into also, that goes from 300 hertz to 3 kilohertz. This makes the wavelengths extremely long. If you were to consider 5 kilohertz, the middle of the band, the wavelength would be 60,000 meters. So there's really interesting propagation effects with this. For hams doing communications in this band, propagation could go thousands of miles from the transmitting antenna. Oftentimes it's kind of like a wire strung on a kite. And even though the antenna is electrically short, you could still get some power. The setups for transmission are actually quite interesting. But for natural radio, many of the natural radio emissions can be detected in the VLF and ULF bands. Obviously, there's other natural radio emissions that occur in the higher bands, but in terms of lightning discharges, most of the spectral powers in the VLF band, such as spherics, tweaks, whistlers, and chorus emissions. Since the VLF and ULF bands are within the human hearing range, Frequency conversion is not necessary and can make receiver and transmitter design very simple, especially receivers. Despite the difficulties in transmission at VLF, successful communications have been made with using narrow bandwidths. There is a fellow who developed a mode called coherent BPSK, and he was able to transmit like 5 or 6 characters over VLF bands, which went thousands of miles, which was pretty cool. Spherics are the most common type of natural radio emission. They're obviously generated by lightning discharges. The energy, the RF energy generated by these are, very broadband, DC to daylight. They occur almost everywhere on Earth. They could be detected anywhere. Lightning detection systems use the time of group arrival method to determine where the lightning stroke actually occurred. And also another interesting physical phenomena is excitation of the N=0 mode of the Earth ionosphere waveguide produces resonant peaks in the ELF band called the Schumann resonances. I don't know if any of you ever heard about that, but the spherical Earth ionosphere waveguide, the fundamental mode for N=0 is around 7 hertz, and lightning discharges excite that. So if you have a frequency plot with a receiving system, you can see those peaks, 7, 14, and so on. So it's actually pretty neat. So if you were to plot spherics on a spectrogram, this is one that I made with SOX. What you'll notice is, the wideband energy, from with this system, it captures to about 22 kilohertz. But what's really interesting, or at least for me, was you'll notice, and it could be very hard to see, and I apologize for that, but there are some spherics where you'll notice that there's little dips in the energy, that certain frequencies are attenuated at the receiving end. These are a little bit easier to see, and that kind of intrigued me. Why does that happen? None of this really means much if you haven't actually heard it. So I'm going to play. So what you'll notice is that, it sounds like the pops and crackles that you normally hear on an AM radio. But this contains most of their energy, so it kind of sounds like sizzling or a bacon frying, things like that. These are interesting enough, but there's much more to it. Tweaks. Some spherics undergo the frequency components dispersed in time as seen at the receiver. These spherics are often called tweaks or tweak atmospherics. A frequency dispersion occurs at around 1.7 kilohertz at multiple harmonics thereof, 3.4, 6.8, and often classified by mode, whereas mode 0 would be the fundamental. Frequency dispersion often occurs in the range of a few milliseconds and seems to be the same length for all modes. On a spectrogram plot, the frequency dispersion is seen as a distinctive tail, starting at 7 kilohertz fundamental. Tweaks take much longer propagation paths in the Earth ionosphere waveguide than spherics, and this accounts for some of their frequency components being dispersed. They are often observed at night in the same way distant AM broadcasts are because of their skywave propagation. It's possible to calculate the reflection height of tweaks, which is actually really cool. There was a paper by a group in Vietnam that actually calculated the height. When audible through a VLF receiver, they have a distinctive pinging sound, similar to the sound of raindrops hitting a metal roof or the rattling of a metal fence. This is an example, and you can see the dispersion that I'm talking about right here. This is at about 1.7 kilohertz, and this is at around 3.4. So this is a mode 1. This is a mode 0, and it's really and also with other spherics, you could see the attenuation here in certain areas, and I'll show you what they sound like. Hopefully it's not too loud. If you notice that pinging sound, that you know, little squeaking sound, that's what you heard, and they come out at night. And during the summer, they're actually very prevalent. So on a nice summer night, you would go out and you actually hear these quite well. This is what I was talking about. These are the multiple modes. Up here we have 2 and 3, sometimes even 8 have been observed. This is another spectrogram. These are all spectrogram plots where it's frequency on the vertical axis, time, and amplitude is indicated in color. And this brings me to one of the things that I'm really interested in, whistlers. When spherics propagate out of the ionosphere, they can take a propagation path thousands of miles through ducts that form in the magnetosphere. This duct consists of solar wind plasma that has aligned itself along the Earth's magnetic field lines. As a spheric propagates through the duct, its frequency components get dispersed in time, ranging from less than a second to a few seconds. Lower frequencies propagate slower than higher frequencies, so the higher frequencies arrive at the endpoint sooner, the endpoint being the receiver. Since the ducts follow the Earth's magnetic field lines, the propagation path terminates in the opposite hemisphere. So what happens is, if there are thunderstorms going on in the southern hemisphere, and the spherics take this Whistler mode propagation, what they do is they travel from the southern hemisphere through the atmosphere, through the duct in the magnetosphere, all around to the northern hemisphere. The frequency dispersion produces a long wavering tone that is characteristic of a whistler. This propagation mode is often called Whistler mode propagation, like I said. Electron density of the duct determines the amount of frequency dispersion, which is called the dispersion measure. Whistlers have very discretely sounding, or whistlers that have very discretely sounding frequency components are called pure note whistlers. Other whistlers can sound kind of breathy or swishy, similar to the sound of air leaking out of tires or something like that, because their frequency components are more spread out. This is a spectrogram of some really nice whistlers. Actually, you could see these are from the Russian Alpha, the Russian Alpha system, and you'll notice the dispersion that you see here. And I have some really nice example of some nice examples of whistlers here. Let's see. I'll play the first one. Now, that kind of blew my mind. That is so cool that this is a naturally occurring that these are naturally occurring and they have such a coherent sound. Here is another example. And you'll notice that little crash at the end. This is actually an example of a multihop whistler, which I'll get to. Now, this is a compilation of whistlers that have been made into one file. These actually gone on at different times, but they're all in this one file. Now, some are weaker than others. So these are whistlers coming from the southern hemisphere. And what you'll notice is later on in the file, you could hear birds. And that's not an accident. That's because VLF antennas are often microphonic, and they act as microphones. And at the time, there was a microphone on the VLF antenna, or a bird on the VLF antenna chirping, and you could hear it through the receiver, which is really cool too. These kinds of receivers are also used to study bat sounds as well. Let's see here. Let's see if I can stop this. Oops. Okay. I actually have the recording goes for quite a bit, but this is another example of whistlers. Stanford did a lot of research in whistlers, and these whistlers were observed in Antarctica at Palmer Station. This is what I was talking about the propagation. So let's say that there's a thunderstorms going on and there's lightning discharges. So the energy leaks out of the ionosphere through a cone, and it travels through this duct all the way around through the magnetosphere. So this is like thousands of miles, and it ends up at this point. And if you're here at A, point B is called your geomagnetic conjugate. to find your own, here is a map of geomagnetic latitudes, and I live in northeastern Pennsylvania, which is right about here. So my conjugate point is kind of down here. Other receivers that were in place. There's some in the UK. There's one in Germany. So their conjugate points are down here, and they tend to get a little bit more whistlers. So another cool thing, when the conditions are right, a whistler energy can reflect back into its original duct and then reflect again at its origin point back to its destination. So it can go back and forth. This is called a whistler echo. Multiple whistler echoes are called echo trains. Each reflection of whistler energy gets dispersed even further, which is really cool. There have been echo trains of over 100 reflections that have been observed. Most of those reflections can't be heard, but they could be seen on a spectrogram. And eventually, as it keeps going back and forth, the whistler just blends into background noise. This is a perfect example. Actually, this is really nice. So this is a triple axis receiving system. This is the E field antenna. This is the B field east-west, or north-south and east-west. So what you can see is these are the original whistlers right here. And you could see the reflections back and forth, and every reflection adds more dispersion, which is really cool. Echo trains are really neat to hear. Now you'll notice each of those echoes do get dispersed, and you hear that, which is really, really, really cool. And then there's often not just one propagation path. There's often many, and these are called multihop whistlers. Whistlers with multiple distinct spheric events can have multiple propagation paths to the same endpoint. Echo trains can also occur on multi-hop paths. And the way to identify a multi-hop whistler is to listen to, for a local spheric that occurs before the whistler. And I have a sample here. See? And then there's another one. Yep, there it is. So this showed this example. Oh no. There's three. So there's a couple different. There were three whistlers, 3 or 4 whistlers there, and both of them and all of them had multiple paths. So there was maybe 2 or 3 ducts from the origin point. Now, in the northern latitudes, this is typically seen in the northern latitudes and probably in the southern latitudes too. You have nose whistlers where you can see it kind of looks like a nose here with distinctive characteristic where Well, this portion here is typically attenuated in a regular Whistler of a lower latitude, but these you could see the whole thing. I also have a sample. This was a recording made by another ham. This also has periodic emissions in there too. Let's see. Oh, actually, I apologize for that. That one was the wrong file. Sorry about that. Okay. Now, other than lightning discharges, the ionosphere also plays a part in natural radio emissions. When solar wind interacts with the ions in the ionosphere, emissions are produced due to a cyclotron interaction. The electron gyro frequency, the angular rotation of electrons rotating in a helix on a magnetic field line, determines the frequency components. Chorus emissions are discrete events that often overlap and are spaced closely together. These often sound like tree frogs or peepers, and they it kind of resembles birdsong at dawn. Dawn chorus often occurs in the early morning hours at dawn. Discrete dawn chorus events can be spaced out on the order of a few seconds or more. Those are called periodic emissions. During geomagnetic storms, dawn chorus can occur more frequently. Dawn chorus also occurs during auroral display events, and that's often called auroral chorus. And it is possible to have your VLF receiver, you could listen to auroral chorus while watching a display, and that's really cool. This is a little bit hard to see, but you can see these emissions right here. You know, they're kind of like tendrils, and these are in the background of spherics. This is some Russian alpha navigation signals. You could see it a little better here, and let me show you the sample. It's a little loud. But you could hear, you know, it almost does sound like tree frogs, and these are due to the plasma interactions. Actually, I thought I had another one. Oh, yes. This one might not be as loud. Actually, in the beginning of this file, it's actually very quiet. But to move on, I'll just go to the next one here. So, triggered emissions. If a VLF event or transmission causes another VLF event to occur, it's called a triggered emission. Originating emissions can often be large spherics or whistlers, periodic emissions or chorus events, even man-made transmissions, like transmitters such as NAA. Triggered emissions have rapidly rising frequency components, and I have a sample here. Well, actually, here's the spectrogram. These are whistlers causing the triggered emissions right here. Now, this sample is not what this spectrogram is. This is another recording. So, what you heard was, I believe that was Omega, the old Omega navigation system, and they caused these emissions. Another type of emission is called HISP, and it kind of resembles thermal noise or fluctuation noise, and that frequency components have random amplitudes. It has a distinct hissing sound. Emissions can either be steady over time or impulsive if it changes quickly, and it's generated by plasma interactions that could be accompanied by whistlers or chorus. I don't have a sample, but here are you could see the HISP band right here. And these are Russian alpha navigation signals. These are tones around 14 kilohertz and 11 kilohertz. I could play a sample. Let's see here. So that's typically what it sounds like. Whoops. There are some VLF transmitters still on the air, SAQ in Alexandersson, Sweden. They use a generator that generates 7.2 kilohertz CW. And they usually, the transmissions occur during Christmas time, different times during the year. That's a picture of the antenna, and that's the generator. These are the loading coils for the coherent BPSK setups. You could see that's a really large loading coil, but they need that's necessary to get the power out, VLF receivers typically have a probe. It's not like a regular antenna. It's a probe with a JFET input stage to convert from high impedance to low, filtering, and some sort of output driver. This is an example of one that I purchased. This is an example of one that I built. I did not design it. It was designed by Stephen McGreevy. You could see the JFET input stage. Filtering right here. This is a pi filter, and this is a microphone output driver. This is an improved model by Sean Corrigan. This is an example of what I built. I added a headphone amplifier and some extra audio outputs for viewing the spectrogram on my iPhone. This is another type. This is the RS4. This was made in the early 90s. It was designed for a NASA shuttle experiment. This is what I built. The board I got from Far Circuits. How much time do we have? 5 minutes. This is the updated version which I built. For B-field receivers, normally it's a loop antenna, a very similar impedance converter, filtering, and some sort of headphone driver. Here is an example built by a group in Vietnam. This is their antenna. This is where the electronics are. This is one that you could buy. This was made by Stephen McGreevy. This is made for stereo listening, so you could have north-south and east-west oriented. This is his antenna right here. And he set this up in the desert to test it. This is another one from Paul Nicholson, who wrote some awesome software. So normally, when you go out and you try to listen for these things, you don't really hear anything exciting at all. You mainly hear spherics, and if it's at nighttime, you'll hear tweaks, but you'll hear Powerline hum, very, very loud. That's why that needs to be filtered out or need to be in a remote area. Usually, at least 5 miles away from power lines, if you live like on a farm, things like that. This is Stephen McGreevy in the desert with his receiver. This is me with mine that I built. But I was actually at my workplace where power lines are underground. There's not enough time, but Powerline hum is the biggest barrier to doing this, and the main thing is that you can't just put a notch filter. You need to use a tracking filter, which tracks the power line frequency as the load on the grid changes. And to record these things, people used tape recorders. I've used digital ones. But the best way is to have a receiver set up outside, feeding to a computer inside. These are the types of interference that you would see in when listening to these emissions. But is it possible to do it at home? So the main thing is to keep Powerline hum out of the receiver and keep it from being injected back into the receiver if you use it for if you have it running inside. So what you need is an automated system. And I use something called VLF RX Tools, written by Paul Nicholson. What we would normally want is something open source, so everybody could do it, and it must be automated. So he has, his is open source. What you do is you feed audio into your sound card as well as the GPS pulse per second signal to timestamp it. It supports triple axis reception, lightning detection, automated whistler and chorus detection, which is really cool. Capture up to 192 kilohertz. Store the data on your hard drive, and also have a stream, a live stream. And his software also runs on a Raspberry Pi, which is really neat. This is an example of a receiver permanently installed outside. The electronics are in here, and this is the antenna, and that's the feed line back to the house. This is a quick diagram of his system. So you have an E-field receiver. I use a Trimble timing receiver, and the north-south and east-west. It feeds into the program called VT card, gets timestamped by VT time, gets filtered, the 60 hertz hum, the tracking filter filters it. These signals get combined by VT cat, and so VT event will automatically detect a whistler or chorus through something called hue transform, and it makes event files. You can do toga measurements, and you can have it streaming as well, which is really cool. So somebody could listen to my stream, or I could listen to it too, without the hum. So the main thing is, without the Powerline hum, you could have clear, a very clear signal. And one last thing here. Paul did not publish this, but Paul has captured Whistler data since 2008, and he uses his Linux systems. And what I wanted you to show you, this is the sunspot cycle right here from 2008 to now. And you'll notice how it very closely correlates to the amount of whistlers received, which is really, really cool. But nobody knows why this is. And maybe someday I'd like to find out. So this isn't published, but this is doing science at home. This is what Paul did. So Paul is he's a great guy. And so I urge all of you to get involved in this hobby, build some receivers, set up these systems. The reference book for whistlers, Whistlers and Related Ionospheric Phenomena, written by Robert Helliwell. He is the father or the grandfather of natural radio. Stephen McGreevy's website is a great intro. Paul Nicholson's website has his live streams from receivers all over the world and his software. VLF.it, that's Mr. Romero's website. That has a lot of great resources and projects. There is a VLF group on Facebook and Yahoo, and the Inspire project. That was what the RS4 came from. That was originally used for a shuttle experiment that did not happen. And that concludes my presentation. I would urge everybody to start reading and learning, and maybe we could figure something out. So,
thank you. Okay, Phil's got a quick question here.
First of all, as a professional person, congratulations. That was an excellent summary of what was going on.
Thank you.
And I'm really impressed at the amount of physics that you also managed to get into these.
Thank you.
One comment and a question. Comment
Yes.
is, you were talking about 60 hertz Powerline hum.
Yeah.
People have actually heard that inside the magnetosphere on orbiting spacecraft about 20,000 kilometers away.
Wow.
The planets...
Wow.
Our power lines are going all the way out. As Jonathan mentioned, you could hear it at the other end of the field line. Well, at some point, it actually had to travel across the equatorial plane of the magnetosphere. You can find it out there. So
Wow.
this civilization is a little loud at these frequencies. The other thing I was going to ask was, your antennas, how narrow bandwidth are they? Because you've got this really lots of coiled wire. What's the fractional bandwidth of a typical system like that?
Well, typically the bandwidth of the receiver is usually between maybe about 10 hertz to about 30 kilohertz. That's the typical bandwidth. Now, with the E-field antenna, it's just a simple probe, just a wire. And the loops I have not investigated all that much. But you can calculate the bandwidth, but I never investigated that.
Great. Any other questions? One more, and then we'll move on.
Yeah, what's the purpose of that station in Sweden and the Russian stuff? Is it submarines, or what do they do?
That was originally used for communications years Yeah, that was in the olden days. I actually forget what its original purpose was, but now it's a UNESCO World Heritage Site, so it's preserved for everybody to benefit from, and it's actually really cool. They just did a transmission this past summer.
Great, thank you. Okay.